Welcome to today's lesson. I hope today, as we are going to look at another very important lesson in physics, we pay particular attention so that we can fully develop the concepts which are required for us to solve more complicated problems. Today, in particular, we'll look at linear motion. So we start the lesson now. So as I indicated earlier, I said today we'll look at linear motion concepts. That is the tools which are going to help us to solve more complicated problems. So as we have said earlier on, linear motion are actually objects which are moving in one dimension, meaning that they are not separated in either two dimensions or more dimensions than one. So these are linear motion objects in movement. And so, first of all, we need to define what displacement is. Actually, displacement is the distance covered in a specified direction. So if you cover a distance and you specify the direction, that is what is known as displacement. It is actually described by both magnitude, which is size, and direction. So it's a vector quantity. So any movement of an object which can be defined by its size as well as direction is known as a vector quantity. So displacement is a vector quantity. And the units for displacement are actually meters. And so speed, now we define what speed is. Speed is the distance covered actually per unit time, meaning that it is actually distance covered divided by the time taken. So it is a scalar quantity because here you will notice that we have not included the direction. So it's a scalar quantity. The scalar quantity is a quantity which can only be defined by the size or magnitude. And speed is measured in meters per second. Now we define velocity. Velocity is actually the distance covered per unit time in a specified direction. So here we have seen that the difference between speed and velocity is basically that velocity includes direction and not only magnitude, okay? Not only the magnitude or the distance covered. Okay, so it is the distance covered per unit time in a specified direction. That is what velocity is. And it's therefore a vector quantity, and it's measured in meters per second. Therefore, velocity is actually displacement over time. Acceleration can be defined as the rate of change of velocity. In other words, we will start from some initial velocity and go to another final velocity. And so we get a difference, final velocity minus initial velocity over time. That is what is known as acceleration. It is a vector quantity and it's measured in meters per square seconds. So acceleration is equal to change in velocity over time, meaning final velocity denoted by v minus the initial velocity, which is shown by u, over time. So it's important that we look at the commonly used equations, which are known as equations of linear motion. We have to familiarize ourselves with these equations because they are actually our tools. Okay, this is a toolbox in linear motion because these are the ones we'll be using actually to solve many problems. And then we have to know them. Velocity, the first equation states as follows. Velocity, which is final velocity, is equal to initial velocity plus acceleration times time. Okay, and if we rewrite this equation, we make A the subject of formula, we'll find that actually acceleration is equal to final velocity minus initial velocity over time. So V stands for final velocity or velocity at the end, and U stands for the velocity at the starting point. That's what is known as the initial. So again, acceleration is equal to final velocity minus initial velocity over time. The equation for displacement or distance is that displacement or distance is equal to initial velocity times time plus half times acceleration, which is A, times time squared. Okay. And then we have the other equation, final velocity squared is equal to initial velocity squared plus 2 times acceleration times the distance or the displacement. So these 4 equations are very, very, very important. We need to practice to know them to enable us to solve actually questions. At times, these questions might not be given, so we have to put them to memory. They are very, very simple equations. Okay. And so, this is the same equation actually, which we have written there. So we are going to now look at the equation in particular to apply some of these concepts, but you will definitely look at only acceleration and the distance covered. And so we'll get this question from a velocity time graph. So the question goes as follows. Calculate acceleration for OA. So they want us to calculate the acceleration from O here up to A. And again, from A to B, from A to B, and from B to C, which is from B here to C. And then they said, furthermore, calculate the distance covered in the first 5 seconds, and then from A to B and from B to C. Also calculate the total distance covered. So we have a velocity time graph. A velocity time graph in the y-axis, it always has a speed, okay? Which, and then the units are written here, meters per second, as we indicated earlier. And in the x-axis, there is time, which is indicated in seconds. There is s here. So this is what is known as a velocity time graph. So if we have a straight line from 0 here to A, it means that we are starting from 0. Okay, on the y-axis, we are starting from 0, and we are ending up to, if you come this way, we are ending up to 10 meters per second. So our initial velocity would be, because the velocity is in the y-axis, our initial velocity would be 0, and then our final velocity would be 10. So if we are to calculate acceleration between 0 and A, therefore would say final velocity, which is 10, minus initial velocity, which is 0, divided by the time it took for this object to move from this point up to A, which is 5 seconds. And therefore, what we need to know is that the gradient, what we are finding here is the gradient or the slope in a velocity time graph would give us the change in velocity, which we said it is final velocity minus initial velocity over change in time. And that gives us actually acceleration. So we have seen here that velocity has changed from 0, it has changed to up to the point A here to 10. From 0 meters per second, it has changed up to 10 meters per second. And therefore, if we are to calculate acceleration from 0 to A, would say acceleration is equal to final velocity minus initial velocity over time, which is equal to, as I indicated, our final velocity here on the graph is actually 10. And the initial velocity is 0 divided by the time it took to move from here to there, which is a change in time. So given this time, it is actually 5 minus 0, which is 5. And therefore, it gives us 10 over 5, which is 2 meters per second squared, meaning that we have calculated the acceleration between 0 and A. Now, let's calculate the acceleration between A and B. Okay, from our graph, we want to calculate the acceleration between A and B. So it means that our starting velocity would be at A here. And what is the point A? You come this side, find that it's 10 meters per second. And then the final velocity would be B. If you come this side where there is velocity, you come again, it is 10 meters per second. So the final velocity is 10 meters per second, as well as the initial velocity, it is 10. And the change in time from A to B, it will be 15 minus 5, which is 10. And therefore, we are saying between A and B, acceleration is equal to final velocity minus initial velocity over time, which is equal to 10 minus 10 over 10, which gives us 10 minus 10 is 0 over 10, which gives us 0 meters per square seconds. So here, when the velocity is constant, by saying the velocity is constant, what we mean is that the velocity is the same. So when the velocity is the same, it means that if the velocity is the same, it means that acceleration would be 0. So we find now the acceleration between B and C. This is the point between B here and C. So in this case, our initial velocity would be at B. Then we go this side, we find that actually the initial velocity is 10 meters per second. And when you come here, if you go to the y-axis here, it is 0. So the final velocity is actually 0 meters per second. What is the change in time? It is 20 minus 15, because it has moved from there to there. 20 minus 15, which is 5 seconds. And therefore, for us to calculate the acceleration between B and C, would say acceleration is equal to final velocity minus initial velocity over time, which is equal to 0 minus 10 over 5, which gives us negative 10 over 5. And this gives us minus 2 or negative 2 meters per square second. So this is a negative acceleration. A distance time graph also can help us to calculate the distance covered. For example, if we want to find the distance which was covered for an object to move from 0 to A, all we need to do is to calculate the area of this triangle, or A and 5, up to 5 here, this triangle, first triangle. So it will give us the distance covered. And therefore, the distance for a triangle for OA is given by calculating the right triangle, which is half multiplied by the base multiplied by the height. And so here the base would be 5 and the height is 10. And so all we need to do now is to substitute here. So we said the base is 5 seconds multiplied by the height, which is 10 meters per second. And this second and this second are going to cancel. So we're going to remain with 5 times 10, which is 50, divided by 2, which gives us 25 meters. Now we need to calculate the distance covered between A and B. The distance covered between A and B. We have to get the area under the curve. And in this case here, we have actually a rectangle. So all we need to do is to get this distance from 15 here to 5, which is 15 minus 5, which is 10. And the height here also from here to there, which is 10. So I'm going to say 10 multiplied by 10 as our area. And yet it gives us a distance. So I'm going to say the distance AB is equal to B times height, which is 10 seconds multiplied by 10 meters per second. So this second and this second are going to cancel. And then we're going to have 10 multiplied by 10, which gives us 100 meters. Then we have to get also the distance BC, the distance moved from B to C. The area under the curve, again, here we have a triangle. And the formula for calculating the area of a triangle is half base times height. Our base here is 20 minus 15, which is 5. And our height, if we go that way, it is still 10. So the height would be 10, and the base would be 20 minus 15, which is 5. So we are going to calculate that one. We say distance is equal to half times base times height, which is equal to 5 seconds multiplied by 10 meters per second. This second and this second are going to cancel. So we're going to have 5 times 10, which is 50, divided by 2, which is 25 meters. The last part of the question, they said we need now to calculate the distance, the total distance which was covered from this point up to that point, from 0 seconds up to 20 seconds. So all we need to do here is to add now the areas we have calculated. The area for the first triangle, the area for this rectangle, and the area for this last triangle. We note that here, even if we are calculating actually the area, but what we are getting are meters, or the distance. Okay, so the total distance will be 25 meters, which we found, plus 100 meters, which we calculated, plus 25 meters, which we calculated, which gives us 150 meters. So I hope this has given us the basic concepts. So next time we're going to look at how we can use the linear equations to solve problems. And also we will also look at more problems to be solved through graphs. So please could you subscribe to my YouTube so that you can receive more of these interesting lessons. I thank you.